Alrighty, welcome back. This is video number 2 of this week. Polar arc length. So we're going to start off by just seeing what the arc length formula for polar graphs is. So it's an integral from a to b of the square root of r squared plus the derivative of r squared with respect to theta. This should look pretty similar to the arc length formula for just normal functions, but what's different is we have an r squared instead of 1. So what are we going to do? First, we're going to do a little proof of where this comes from by, again, looking at the arc length of the curve given as just a function of theta, and we are going to look at our indices alpha and beta as theta values. We are also going to assume that the curve is traced out once for the proof, just as we did with tangent lines, not for tangent lines, but for parametrics. And just like we did with the tangent lines and polar coordinates, we're going to first write out this polar graph as a set of parametric equations, x and y, where x is equal to r cosine theta and y is equal to r sine theta. And now actually, because we are rewriting the polar graph as parametrics, we can use the parametric formula to find the arc length. And so what we'll need is the derivatives of each piece for these computations, and we are just again doing product rule to get the derivative of y and the derivative of x. And we are going to do a little bit of manipulation. So when we go back to the original equation for arc length, we have this r squared. And we know that r squared is equal to x squared plus y squared. So what we're going to do is we're going to say, I wonder what dx squared plus, dx d theta squared plus dy d theta squared, what is that going to equal to? So we'll do a little bit of manipulation. So we're starting with, here is dx d theta. We're going to take the whole thing and we're going to square it. And then we're going to take dy d theta. We got that, and we're going to take the whole thing and we're going to square it. And we're going to do a little bit of algebra. And that takes us to our next line of dr d theta squared times cosine squared theta minus 2r dr d theta cosine theta times sine theta plus r squared sine squared theta. That was a little bit of a jump. So if you want to take a minute to work through some of the algebraic and trig work, please do. I'm missing the other half, plus dr d theta squared sine squared theta plus 2r dr d theta cosine theta sine theta plus r squared cosine theta. Woof, that's a lot. So that's like the first step, is expanding that out, doing some rewriting, doing some simplification. And we want to simplify even further. Basically, we want to group terms. So if we can notice here that we have dr d theta here, dr d theta here, dr d theta here, dr d theta here, we can start to do some clumping and restructure. This is going to be equal to dr d theta squared times cosine squared theta plus sine squared theta. So this comes from here and here. And then we also have some r squareds here, r squared here, and r squared here. So we'll have r squared times sine theta, sine squared theta, cosine squared theta. And then you might be thinking, well, what happened to the other terms that we highlighted? So that was here and here. I'll give them another color. Well, one is a minus. So minus 2r dr d theta, cosine theta, sine theta. And we're adding the same thing, so they're going to subtract to 0. So that's why it disappears. Now, from trig, we know that cosine squared plus sine squared is equal to 1. So this nicely simplifies to just r squared plus dr d theta squared, which is awesome because this is so much simpler than this mess. So what is this? Why is this important? Well, this is taking us back to, remember where we started, what x squared plus y squared equals r squared. Well, maybe derivatives of that is interesting. And so we're exploring that. And so this ends up being the arc length formula. So then the arc length formula is going from some alpha to some beta, the square root of r squared plus dr d theta squared d theta. So we're just interested in what should we be, when we take the square root, the length of that arc that's created. So that's kind of a mini proof. It's not super full, but remember that the arc length in general comes from the idea of the Pythagorean theorem or the distance formula. So let's use the formula. And again, you do not need to memorize it. Math is about making connections, not memorizing. So let's find the arc length. You can't see that. There we go. So find the arc length from theta equals 0 to 2 pi for the curve r equals 2 minus 2 cosine theta. So what do we need in our formula? We need r, we have it, and we need dr d theta. So we need to just do a quick derivative. That will be just 2 sine theta. So the length of the arc is going from 0 to 2 pi. The square root of 2 minus 2 cosine theta squared plus 2 sine theta all squared with respect to theta. And now you can actually do a little bit of expansion and simplification. Plug in, take the antiderivative, plug in your integral, and you actually get out that the integral of this arc is 16 units, which is nice. And fun fact, that's actually my favorite number. I'm gonna put up, I think, as long as you know what the formula is, we really just need to apply it. So I'm gonna put up 2, 3, 4, A and B. For number 4, it says set up, but do not evaluate an integral. For number 2, calculator is okay. For number 3, try without a calculator. All right, in 10 seconds, I will pull up some answers. Okay, so that's 2, 3, 4, A, and B. All right, come to office hours with questions about this. Really, just use the formula. And you're good to go. All right, I'll see you at the next video for polar area.